So basically, the concept of subspace is that it has to satisfy these three properties. This is called closed under addition. This one is called closed under scalar multiplication. So if you have something like this, so this is a line through origin. This will be a subspace of R2. If I have something like this, this is not a subspace. Do you guys see why for each of this? You just need to check these conditions. Okay? You check those conditions and see whether it's satisfied. This one is obviously not a subspace because it has
contain the zero vector.
It doesn't contain the zero vector. Yeah. Okay, that's the concept of subspace. Let me know if you don't want me to erase it, you want me to wait, okay? Otherwise I'm going to keep talking and keep erasing. Let's say we want to solve something like this. Solve when we solve this, okay, so this is the same as solving this. Where A is 1, 1, 2, 2. So when we solve this, you do something like this. I'm skipping some steps because I think you guys are very good by now. Can you guys see that?
Yeah.
Yes.
So we call this null space of A is the span of this vector. Now the null space of A is the span of this vector. So if you draw it, it's this line, right? That line is the null space of A. So null space of A is this is a subspace of R2. Okay. Column space of A. What does column space of A mean? Column space of A is it's spanned by the columns of A. So in this case, it's the span of But these two are actually redundant, right? So it's actually just this one. So in this case, the dimension of null space of A is equal to 1. The dimension of column space of A is also equal to 1. And in general, we have this thing called the rank theorem. The dimension of column space of A is called the rank of A. The Brine Theorem say that the rank for A is an n by n matrix. The rank of A. The rank of A is dimension of column space of A plus the dimension of the null space of A. What's it equal to? Is it m or n?
N.
It's equal to n. Because in general, this matrix look like this. Okay. It's a n by n matrix. Dimension of null space of A is actually equal to number of free variables. Okay. I'm just keep throwing results at you because this is a review, okay? It's the number of free variables in the RREF, okay? And the dimension of column space of A is equal to the number of pivots. So of course, these two add together will be equal to the number of columns. N is the number of columns. Number of columns. Number of free variables. And this one is number of pivots. Are we okay up till here? You guys need to let me know whether this is useful or not, okay? If it's not,
useful.
yes?
Yeah, it's useful.
Yeah, so it works.
Okay. Okay, can you tell me what's the answer? What's the rank of it?
Three?
What was that?
3?
Why is it 3?
At most, it could have 3 pivot columns.
I already told you there's 5 free variables.
Oh, I didn't. Oh, I see. So then 2.
Is it okay?
Yes. I didn't see the dimension null a equals 5.
Yeah, it's kind of good. And it's too. So you just need to be able to apply that theorem correctly, okay? Make some deductions sometimes. I'm going to go back to here, okay? I'm going to go back to this example. And change this to a little bit here. Okay. So if you have something like this, right? Now remember that when we have ax equal to 0, we end up having the solution to be this. If you still remember, this is the null space, right? You guys remember that? The solution look like this. This is solution. And now if I have this like this, is this equation, is this consistent? So if I have 1, 2, 1, 2, 4, 8. So what end up with 1, 1, 4, 0, 0, 0. So do I have is it consistent, this system?
No.
No? Can I get some answer?
Yes.
Yeah, it's
It's
consistent.
consistent. So x2 is equal to x2, x1 is equal to minus x2 plus 4. So the solution space here so this solution space is the same as the solution space we have earlier.
Isn't it -4?
Positive 4. Because this 4 is on the other side.
Oh, okay. Yeah. Okay.
Is it okay?
Yeah.
So this is in general true. So you have a system, okay, and if this is consistent, then the solution space will be the same as the solution space for the corresponding homogeneous equation, but translated. You take this guy, add 4, 0. So this guy is the solution for this. Okay, so it's a translation. In general, this is true. I mean, you can have A can be, doesn't have to be 2 by 2, it can be larger. So in some sense, this one is a particular solution, right? Just like this is exactly the same as in differential equations. Okay, you have a differential equation. You have the homogeneous part. Homogeneous part, usually you have this one, you have a parameter, which is the constant C, C1, C2 thing. Okay, depending on the time. How many functions are there in the fundamental solution? And then you have the particular solution. The particular solution, I mean, the differential equation terminology is yc plus yp, right? So this part, yc is this guy, yp is this guy. You just translate the yc and you get the general solution. So it's exactly this. This is exactly what's going on. Okay. Are we okay? Okay. Feel free to ask questions, guys. This is an example that we did earlier in class already, okay? I have done this example before, just reiterating this. So if I want to solve ax equal to 0, how do I do this? I put the a, put a bunch of 0 next to it. So basically, what I do is that I take this a, I put a bunch of 0 next to it. This is my a. I put a 0, 0, 0 next to it, and I do RREF. Let's say I end up with this. So what will be the rank of this matrix A? Can you see from here what's the rank of A?
2.
Rank of A is 2. Dimension of null space of A. What's dimension of null space of A?
3.
Okay. So you can actually what is the null space of A? It's going to be spanned by something which is the basis. Okay. This is the basis for the null space of A. And it's going to be I can do it in my head. So this one will be x2 equal to x2, x3 equal to x4 equal to x4, x5 equal to x5. So x1 will be 2x2 plus 4x4 minus 3x5. You guys with me? X3 will be minus 2 x4 plus 2x5. So then you write down these columns. Will be 2, 1, 0, 0, 0. And this guy is 4, 0, minus 2, 1, 0. Are you guys with me? Minus 3, 0, 2, 0, 1. Okay. And these guys are linearly independent. These three are linearly independent. So this guy form a basis. null space of A. How do I know this is linearly independent? Because this guy has 3 pivots. Can you see that? 1 0 0 0 1 0 0 0 1, which come from x5 equal to x5, x4 x equal to x4, x2 equal to x2. Okay, so those guys will get me the 3 pivots. So if you look at this, write this as a 5 by 3 matrix and do RREF, you will end up with these 3 pivots and the other one will be 0 out. Okay. So what would be a basis? So the column space of A will be spanned by what? Now these guys are these two are the pivots, right? These are the pivot columns. Okay. Do I write these 2 columns here?
Oh,
No.
No. What do I write?
the corresponding columns in A.
The corresponding columns. Very good. You guys are very good.
Why is that? Why do you have to write the corresponding columns for A?
Because we have talked about the column space of A. The column space of A is spanned by the columns of A. Okay, that's the definition of column space. Column space is the subspace spanned by the columns of A. But some of this, I mean, you can write all 5 of them. Okay, you could have write all 5 of them, but some of them are just redundant because not all of them are. If you write all 5 of them, it's not going to be a basis. If you do it like this, this one is a basis. Okay, because these 2 are linearly independent, and the other 3 can be obtained from these 2. Okay, why and how is through the following. I'm going to look at these 2 matrices. One is my A. Now I'm going to call this guy B. I'm going to call this matrix B. Okay? I'm going to call this matrix B. What happened is the following. AX equal to 0 and BX equal to 0. These 2 guys has same solution sets. You guys know what I'm talking about? Because you are just doing row transformation, of course, the solution set of this is the same as solution set of that. That's the whole premise of doing this RREF stuff. They have the same solution sets. Because they have the same solution sets, you can think of this as x1a1 plus x2a2 and so on plus x5a5 equal to 0 if and only if this guy these B's are the columns of B, okay? Columns of B, I call this little b. These are just this and this are talk about the same thing, just written in a slightly different way. But this one reveal a little bit better because that means the linear dependence. That means the linear dependence. Okay, they have the same linear dependence. What this is saying is that between columns of A is the same as, I mean, this is not very precise, the terminology, but I hope you understand what I mean. Columns of B. So what this is saying is the following. If I look at the matrix B, I actually know that from here, I know that the second column, I'm going to write it down here. I know that B2, the second column, this guy is equal to -2 times B1. Okay? And because of that, over here, you can see that this second column, A2, is equal to -2 A1. Can you guys see that? Yes, no? Now, how about this? How about B4? B4 is this, right? This is B4. It's negative B1 plus 2 B3. So because of that, A4 is negative A4 plus 2 A3. Can you guys, you can check this guy. Sorry, I say this is a 1 here. Negative A1. 2A3 minus A1 so give you this column. Are you guys know what I'm trying to say? The dependence relationship between the columns of A is the same as the dependence relationship between the columns of B. Can you guys help me with this A5 stuff? A5 will be, A5 should follow the B5. Okay, over here, B5 should be what? Can you see this B5? Should be how many times B1?
3.
3 times B1 minus 2 times B2. So A5 should be 3 times A1 minus 2 times A2. You can check this if you want, okay? Are we okay? You guys good?
So could you take one of the other columns of A instead of one of the red ones you circled?
You can, potentially, yeah. I mean, you can take.
For the column of A, the span of, it could be like 3, 1, 2, and 1, 3, 8 instead or something?
It can be, yeah, probably, yeah. You can do that if you want. But it doesn't, but if you want to write the other ones as linear combination of the 2 that you have chosen, then it's a lot more difficult when you write down for you to write down the relationship. Because here I can easily write down the one which is not circled, not in red, the A2, A4, A5 as a linear combination of these 2. It directly comes from here. Yeah. You potentially can choose 2 other ones.
Okay, but that one's just the easiest.
Yeah, in some sense it's the easiest, yeah.
Okay, thanks.
No, just keep moving along, okay?
Luca had a specific question. Maybe we want to go over. I don't know how long that one will take.
You have a specific question?
Yeah.
Okay.
Could you go over how to in the last section that we just submitted? Could you go over how we identify which vector is a maximum attractor / repeller on a graph?
Okay. Oh, by the way, you guys, I hope everybody understand that on Wednesday you just log in to campus at 12:45, and then you can see the test, and then you do the test, and you have to submit it before 2:15. Okay. Otherwise, it doesn't let you submit it. Okay. Through campus. So, Josue, you are asking me about so you don't understand the definition of attractor and repeller?
No, more like how to identify it on a graph.
How do you identify on the graph?
Yes, part of the like 3 of the homework problems asked. I understand how to tell which one it is by the value of the eigenvalue.
Oh, okay.
Positive, negative, both positive. But on one of the questions, it was asking to
Okay.
select which graph represents this.
Okay. I'll share the screen. I'll show you some pictures. Okay. Are you guys seeing my screen now?
Yes, Professor.
Okay. Attractor, Josue, attractor is when all these arrows are going to the 0, 0. Then the origin will be an attractor in this picture. Is it okay? Now, a repeller will be similar, except that these arrows all of the arrows are going in the opposite direction. So this one is in the opposite direction. All these are in the opposite direction. That will be a repeller. Saddle point is this. I don't have a specific picture for the repeller. Okay. But can you see that this is attracting towards here, going to origin? But the other direction of the other eigenvector here is going away. It's repelling. So one attracting, one repelling. So it's a saddle point. Did I answer your question or not? You want me to? Do you want to show the picture to me? I can actually let you share it.
Let me see if I can pull it up.
I'll try to see whether I can let you share, okay?
Okay. No, there was one homework problem where I understood how to that works, but I feel like it was missing one of the vectors.
I think I'm letting you share now, letting everybody share.
All right. You have office hours today, correct?
What?
Do you have office hours today?
I do, yeah. But
Okay.
can you share it now?
I'm pulling it up.
Okay.
What's this one? Okay, here we go.
You probably have to somehow click some button to share though. I just enable everybody can share.
All right. All right, there you go.
Okay. So if it's a repeller, so it's going away in both directions, right?
Right. And so,
So this part, A will be a saddle point. A will be a saddle point. B is also look like a saddle point, right? Because
okay.
for A, the red one is going away. The blue one is going in.
Okay.
Okay.
And then, let's see, maybe I need to make this bigger.
So C is the correct answer?
Yes. 1.
1, 1. How about the
Right.
one? How about the 1/4 and 1?
Yeah, that's where I didn't know why this.
They probably need to draw the other one. I don't understand.
Okay. Okay. So, all right. I thought it
Yeah.
was missing something else as well.
Yeah. There need to be the other one. I don't know why it's not drawn. It may be the problem with the software.
Okay. Good.
Sorry.
All right. Then. Oh no, that makes more sense then.
Okay. They need to have the other eigenvector.
Okay.
I don't know why it's not there.
Okay.
Someone is chatting. Oh. So
Ah.
direction of greatest attraction. Yeah, so Mahima is right. The largest vector.
Oh, because it's
bigger.
yeah, 2/3.
Oh, I see. Can you read the chat, guys? Mahima is asking you. It's explaining to you why it, because it say that it's only say that it's say greatest magnitude. That's why it's only a single vector. So it's not drawn wrong.
Oh, okay.
It's just that it has something that we missed.
I see.
Is it okay?
Yes. Thank you, Mahima. Thank you, Bryce.
Okay. Okay. Now you can unshare your screen now.
Did I? I did, right?
Oh, you did already.
Yeah.
Okay. All right. So let me just go on, move on. I may be jumping around a little bit, okay? Because I'm not going to be able to linearly just keep going and then cover all the sections. I'm going to run out of time. So I will be jumping around. So I have okay, so here. Let's talk a little bit about determinant. What would be the determinant of A? What would be the determinant of A here? What's the definition here? How do I compute?
AB minus BC.
AB minus BC. Okay, it's determinant of A. And if I have, so A inverse, so if determinant of A is not equal to 0, then you can talk about A inverse. How does this other part look like? Okay. So the effect of elementary row operations on determinant of A. So here A is an n by n matrix. Effect of elementary row operation on determinant of A. So when we swap, so when you have A, you have B here. If this one is swap, 2 rows. How are these two related? How are these two related? Are they equal? You guys remember?
The negative.
It's negative. Scale, maybe I just write this. Li equal to K Li replaced by K Li. Multiply a row by K. So determinant of A of B. How is it related to determinant of A? Anybody? How is it related?
Multiply it by K.
Multiply by K. How are these related? Row replacement operation. How are they related?
They're equal.
They are equal. So this is essentially. So you can use this to actually compute determinants. Okay. So if I have let's say A is 1, 2, 3, 4. Okay. How is determinant of, let's say, 5A related to determinant of A? How is it related? Anyone?
5 times the determinant of A.
Is it correct? Is it correct, guys? It's actually not 5, it's 5 squared. Do you guys understand why? Because here is multiplied by 1 row. This guy 5 times 8 is multiplied the entire matrix. So both rows are being multiplied. You guys know what is going on? It's slightly tricky.
I see it now once you put the numbers in.
Okay. So you need to be slightly careful. When you put a 5 in front of a matrix, the entire matrix multiplied by 5, not just one row. So you'll multiply both rows by 5, so it's 5 squared.
So is it essentially 5 to the power of n?
Yes.
Yeah, okay. Thank you.
Yeah. Yes. Yeah. Depends if it is an n by n matrix. Can you guys tell me which one is true? Which ones are true? Which ones are false? Some of that is false. At least one of them is false. I mean, I'm talking about in general. Okay, these are general matrix. Okay. So A, B are both n by n matrices. Okay, the first one, is it true? The determinant of product is the product of determinants. Did we encounter this before?
Yeah, it's true. I think it is.
It is true. I never prove it, but it is true. The proof is long, and I never really try to prove it. It can be proved by using the elementary matrices. How about this one? What do you think about the second one?
I'm guessing no.
Okay. Do you have a counter example?
Could we find the transpose of 1, 2, 3, 4?
Okay.
Or I don't know. It is a guess.
Yeah, no, that's fine. That's fine. It's okay to play around with it. Okay. Usually this is how I attack a problem. Let's say if I think it's no, then I start to try to do counter example, right? If I try a lot of counter example, and none of them work as a counter example, then I start to think it's probably true. Then I start to try to show why is it true. You know what I'm saying?
Yeah, that makes sense.
So this one, do these two have the same determinant? It does have the same determinant, these two. Okay. Remember that when we talk about computing determinant, we can expand along any row or any column. Do you guys remember that? When we compute determinant, we can do expansion along any row or any column. Since the transpose is just swapping row and column, So the row of one is the column of the other. So you can, so that's why this one is actually true. So you can, for A, you can expand along a row, the first, let's say first row. For A transpose, you will expand along the first column. And then the computation become the same. Is that okay? Anybody, what do you think about this one, guys? Oh, this is assuming determinant A is not equal to 0. Okay, otherwise we can't talk about that. This one is actually true, and it's actually not too difficult to figure out from what we have already. Okay. So, but what is A times A inverse?
I.
A times A inverse is I. So this I is the same as determinant of I. What's the determinant of I? What's the determinant of identity matrix?
1.
It's equal to 1. So 1 is equal to, now I have 1 is equal to determinant A. Determinant A inverse. So I can put this to the other side. Okay. How about 4? So this third one is true. So this also good. How about number 4? Determinant of sum is the sum of determinant. Anybody remember this?
I think it's false.
Yeah, this one is false. And we can easily get some kind of example. Okay. Let's say A is equal to 1, 1, 0, 0. B is equal to -1, -1, 0, 0. Then determinant A is equal to 1. Determinant B is equal to 1. Determinant A plus B is determinant of a bunch of zeros. 0. Okay. Okay. So 1 plus 1 is 2, but this one is 0. 0 is not equal to 2. How are we doing, guys?
Good, good.
Okay. I am going to just keep moving along, okay? I'm going to go to some chapter 5 stuff. The 4 and 5 stuff. Also called probability matrix. let's say something like this. 0.1, 0.2, 0.7, 0.4, 0.5, 0.1. This is a stochastic matrix or probability matrix. So, P, we'll just call it A then, okay? A. Sum of each column. 3.1. Okay. So the entries, all entries, maybe I just write here, all entries. This type of matrix is called stochastic matrix or probability matrix. It's talking about transition from one state to the other. So these are the states, okay, 1, 2, 3. So you will have these diagrams, 1, 2, and 3. So we'll have these different arrows. How do you go from one state to the other? These are the state diagrams. This state diagram, these are the probabilities. From state 1, so this is from, and this one is 2, from here to there. From state 1, there's a probability of 0.1 staying in state 1, 0.2 going to here, 0.7 going to here. You guys know what I'm doing? That's what that matrix means. From 2, go to 1 is 0.4. To itself is 0.5. To 3 is 0.1. From 3, going to 1 is 3 to 1 is 0.2. 3 to 2 is 0.3. That is the state diagram. And this is called transition matrix. For the Markov chain, for this type, so we have this concept of steady state or stationary distribution. Okay, and that is the solution of AX equal to X. Okay, stationary state in the sense of when you get to the, you find the X where you go to the next state is still itself. Okay, so as time goes to infinity, this guy, because what you do is that you start out with x0 and then you have ax0 and you have a squared x0 and so on. You keep going. As time goes to infinity, it will settle on this state. What it settles on is going to be the solution of this equation. Why does this always have a solution? Okay, so we can actually show that this always have a solution. The reason is that the reason that this always have a solution, okay, ax equal to x always has a solution, a non-trivial solution. Another way to say that 1 is the eigenvector, so you can always find an you can always find an eigenvector x corresponding to the eigenvector 1. Can you see that? Say 1 is the eigenvector. One way to see this is that when you're trying to solve this, what you are doing is the following. You're trying to solve a minus ix equal to 0. Okay, what is a minus I? A minus I, for a minus I is going to look like this. What is sum of each column of a minus I? Sum of each column of A is equal to 1. So what would be sum of each column of A minus I? This, the sum for it. So this guy, the sum is 1, right? For A itself. How about for I? The sum is what? The sum of each column is what? For the identity matrix. You guys don't know what I'm talking about. Let's say I have an identity matrix. I add up this column. What do I get? What is 1 plus 0 plus 0?
One.
That's 1. What is 0 plus 1 plus 0? What is 0 plus? It's also 1. All these are 1, right? The sum is 1. So what is the sum of each column of A minus I? You can use this as an example to help you to see it. If you subtract 1 here, subtract 1 here, subtract 1 here, when you add this up, what happens? Can you see that this is 0?
Did the quality drop for anyone else?
Yeah,
Yeah.
it did very much.
Yeah, the quality dropped a lot. It's hard to read the board.
Okay. Maybe I just have to wait a little bit. Is it better or is it the same?
It's the same.
So I get out and get back in? See whether it helps? I'm going to get out and get back in, okay? You guys stay on, okay?
Okay.
Yes.
Yeah,
Okay.
better for me too.
Okay. Sorry. The internet. I already have pretty good plan for my Comcast thing. But sometimes I have a lot of people. I don't know. I mean, in general it's better now. No wonder even I ask you 1 plus 0 plus 0, you don't know, you don't not answering me. Okay. So can you see this? Each column now add up to 0. You have A minus I.
Yeah, that makes more sense now.
Okay. All right. So the RREF of A minus I at least one row of zeros. Okay. So that means
Oh no.
that means there's at least one row. So that means there is at least one row without pivot. That also means that there is at least one free variable in the solution of a minus I x equal to 0. Okay. So you can always, what it means is that when you solve for this, you will always get a non-zero answer. Okay. And you can take that non-zero answer, okay, and that will be your, that essentially will be your steady state solution. Okay. Any other question?
Hey, how come you didn't put in the eigenvalue?
What? Say it again.
How come you didn't put in the eigenvalue lambda anywhere?
Because the eigenvalue is 1. For when we talk about the Markov chain.
Okay.
You don't use eigenvalues for Markov chains.
Okay.
This is actually, this is the eigenvalue is actually 1 when we solve this. When we solve for the stationary, for the steady state vector. The eigenvalue is actually 1. But when we first do that, it was in chapter 4, and we didn't use the terminology. Because we haven't done chapter 5 yet at that time.
Okay.
Any other questions? I'm kind of running out of time. So do study the study guide, please. Okay. I wasn't able to review everything. It's a lot of stuff. But I reviewed the earlier stuff. Hopefully you still remember the chapter 5 stuff. Is there anything that won't be included in the exam? I think everything in the study guide is potentially in the exam. Those sections. The sections in the study guide.
Are we submitting photos or a PDF?
Either one is fine.
Okay.
Whatever is convenient for you. Make sure you have enough time to submit it, okay? Please. Because if you miss that deadline, that's not good. Any other questions?
So, Professor, is there any chance that if we pass the time that we can apply for resubmit the photos?
I don't know. I really don't know how to handle that.
We could email you it.
Is that possible?
If you really just completely miss it, okay. Okay, if you miss it, you email it me. But don't email it me the next day though, okay? I'm talking about the
Okay.
next,
Yeah,
I'm
within
talking about the next couple-
reason, right? Like
yeah,
like a
the next couple of minutes, I'm talking about.
Okay. That makes
Okay.
sense. Yeah.
Okay, I'm really talking about the next couple of minutes.
All right.
Okay.
Thank you, sir.
Yeah, because I mean, I have to set some deadline. I don't know how. I mean, if I say I give you 5 extra minutes, then it's you still can miss it, right? So you know what I'm talking about. So you just need to reserve some time.
Someone asked in the chat, can you submit multiple times tomorrow, like during the duration of the test?
I have no idea. Anybody know? Does anybody know?
I think you can resubmit as long as it's within the allotted time.
Okay.
Okay, yeah, because that's what it usually is on Canvas, right?
I mean, I have never used it. This is the first time. So yeah, I mean, if you say you can resubmit, then you probably after each question you submit it. Is that what you're happening?
For me, it'd be like, okay, at 2 o'clock, I take pictures and send it. And if all goes smoothly, then I might have a little more time to do more problems and then take it pictures again and send it. But if I have technological issues at 2 o'clock, then I'll have it. I have time before 2:15.
But when you okay, maybe we can talk through this. When you resubmit it, do you have to submit the earlier ones also? Do you guys know?
Oh, do you mean like if you submit each question separately? But I don't think you can do that.
It doesn't work, right?
I
So
think
you can submit all 10 questions, okay, maybe at 2 o'clock, and then later on you make some corrections, and then you resubmit it again, and it will override the first one. Is that what happened?
I think so, yeah.
Okay. You guys have more experience than me on this. I really don't know how it works that well. Okay, so when you resubmit it, don't just submit the new one. I mean, you basically have to resubmit the whole thing. So the earlier things get wiped out, basically. Is that what happened?
Yes.
Okay. Yeah. Okay, so hopefully everybody understand that. Any other questions? For me, it's also a little bit new, this thing. Okay. So, but I think it will work okay for us because this thing is a little bit more conceptual, unlike in some other classes. In some other classes, if I ask you to compute an integral, you can probably just type the stupid thing into Wolfram alpha and then you have the answer. But this linear algebra is a little bit more conceptual, it's a little bit more difficult to do. I actually try to get some of the question into Wolfram alpha and just make sure you don't get too much out of it. Okay.
Are you curving off the highest grade or off a set amount?
I'm trying, as I said, I have promised you that at least one of you will get 100%. That means I will be curving on the highest grade.
Okay.
Yeah. I think that's kind of reasonable. I mean, you can all agree to everybody just submit all. You can all agree between yourself, everybody will get 0, then everybody will get 100. You know what I'm saying? If the whole class gets 0, I'll have to give the whole class 100. I'm just kidding, guys, okay? Because there's no way that you can agree everybody gets 0. Do you think it's fair, or you want me to do it, or you think some other way would be better? You have no response.
What do you all think? Because my thing is, if it's open note, isn't it very likely that someone gets 100 anyway?
Oh, I see. I see.
So a flat amount makes sense to me.
I don't want to do I don't want to do a set amount because I don't want someone to be way over 100.
Or just don't. Yeah, if you get 100, then you get 100, right? Like
Yeah, I can probably squeeze the range a little bit. I can do this, okay? I can potentially do this. Here's another way to do this. Here's another way to do this. So original score and revised score. Okay? Okay. So what I can do is the following. I have 100 and 100 here. It's 1 pawn. If original you get 100, you still get 100. Okay. And then I will have the second pawn is going to be here. This is called X and this is called Y. So here I have an X bar, which is the average. I take the original score, compute the average. Okay, which is called X bar. I can put this guy here at 75. And then will be my curve. You guys know what I'm talking about? So I guarantee the class average is 75. Is it bad? Okay, I change it to 80 then. Or 78. I need to pick a number here. You know what I'm talking about?
77.5.
Okay. Okay, I give you 78 then.
Well, it's
Okay.
better if it's lower, right?
Huh?
Ooh.
No, it's better, it's high. This is a Y coordinate. So I
I see,
basically force the class average to be 78.
If you're doing that instead of the bell curve, that means more people will be getting A's, right? Instead of less people. Is that since you're doing it like a line?
No. Whether you get A eventually is based on all this score and then compute according to the formula according to the formula on the syllabus to determine. But this is just talk about this test. This is just talk about this test itself. So this is one way to curve it.
This always helps you unless you get 100, right?
Depends on the actual class average here. If this X bar is like 90, then that will be terrible. Then I'm forcing everybody to be lower. You know what I'm saying? Okay, so what I can do is that I'm going to do this, okay? I'm going to do the following then, okay? I'm going to curve according to this graph only if it I need to make sure I'm not too generous. How about this? Okay, only if the class average. If the class average is bigger than 78, I'm not going to curve you lower. How about that?
Yeah.
Is it okay? If everybody is doing really well, the class average is 95%, I won't touch it.
Yeah, thank you. That sounds better.
Okay. If the class average is exactly at 78, then nothing will happen. If the class average is less than 78, then I'll make it 78. Is it okay? That sounds pretty fair.
What everybody think, put it in the chat. We have 2 people speaking for everybody. We gotta get some more input.
Okay, the chat says it's fine.
Okay. All right, that's good.
It's okay? I don't think, I think it's okay. Now this is being recorded, so I mean, we have a record, okay? So we're going to just do this.
And you said that the midterm, it's going to be long so that to prevent us from having time to cheat. Is that what you said last class?
Yeah, it's a little bit long. So I would think that this thing will actually help you. I think this will help. I think this will help you. I think this will help you. So when it helps, it helps everybody, okay? So it will help. So it really depends on the slope of this graph. If the actual class average is less than 78, the slope of this graph will be bigger than 1, and it will be to your advantage. But if the slope of the graph, okay, if this slope of this graph is less than 1, I will not change anything. Is it okay?
Yeah.
So everybody benefit. If I actually curve it, everybody uniformly benefit. Unless you get 100%, then you don't get any benefit. Is it okay?
Sounds good, Professor.
I think it's pretty reasonable. I have done something like that before, but it's afterwards when I curve it. You guys good?
Yes.
Okay, so we agree on 78, okay?
All right, thank you.
Okay, I'll see you guys. On Wednesday, I will be logging in. I will log into Zoom. So you don't have to log in, but if you need clarification, okay, then you can log in. I'll be there.
Thank you, Professor.
Thank you.
Bye,
Okay,
everyone.
see you. Bye.